Hello, everybody. This is the second part of the second lecture of week 9, and we're still discussing confidence intervals. First part was we were talking about confidence intervals on the mean and on differences of mean, and now we're going to move on to talk about confidence intervals on proportions. Okay, so as I mentioned earlier, proportion is basically our probability of success. If you remember, our Bernoulli trials had a probability of success, which we called P. So in this part of the course, this is commonly called proportions. So we're talking about proportions of populations that are going to vote for a particular party, that sort of thing. And basically, it's the P then is the probability of voting for a particular party as opposed to not voting for a particular party. So how do we estimate P? Basically, in practice, we would phone up 1,000 people and ask them who they're going to vote for and record a success. If the person phoned said yes, they're going to vote for that party, and a failure if they said no. And then all we have to do is count up the number of successes and divide by the total number of people that we phoned up to get an estimate of the proportion or the probability of success. So P hat is the number of successes divided by the number of trials. And we know from earlier in the course that the number of successes is just n sub n. So the number of successes in n trials we called n sub n. And now we're just dividing that by the number of trials to get an estimate of the probability. If you recall, the expected value of n sub n was n times p, so the number of trials times the probability of success. And if I just solve that thing for p, I get p is equal to the expected value of n sub n divided by n. And what we're going to do is just approximate this by n sub n, the actual observation, divided by n. So the n sub n, which we counted, is an estimate of the expected value of n sub n. Okay, so that gives us p hat as our estimate. So our confidence interval in the true proportion p is therefore our usual form, something plus or minus something times something. In the first something, we put their estimate of what we're taking the confidence interval on, and that's the true proportion p, and our estimate is p hat. For proportions, we're always going to use z, so we're always using the normal approximation to the binomial of the n sub n. And so we're going to use z there, so it'll be z alpha by 2. And then the last thing is just as usual, the standard deviation of whatever we put in the first set of brackets here. So standard deviation of hat p hat. Okay, so let's take a look at that. The standard deviation of p hat is, we start with the variance. So the variance of p hat is the variance of n sub n over n. The 1 over n can come out front, and because it's a variance, we square it. So we got 1 over n squared variance of n sub n, and if you recall, variance of n sub n is npq. So altogether we get the variance of p hat to be pq over n. But the problem at this point is that generally speaking, if we're trying to get a confidence interval in the true proportion, then we don't know what the proportion is. If we do know what the proportion is, then there's no need to do any of this. We already know it. We don't have to estimate it. So we don't know what the proportion is, so we don't know what value to put into this calculation of the standard deviation or the variance of p hat. So what we do is we approximate this variance pq over n using our estimated parameter p and p hat, and 1 minus p hat is q hat. So we get the variance of p hat is approximately equal to p hat q hat over n. And of course, we have to remember we have to take the square root to get standard deviation here. So our confidence interval becomes p hat plus or minus z alpha by 2 square root of p hat q hat over n. Okay, so just some notes. I've already kind of mentioned this. We first of all will always approximate n sub n using the normal distribution. There's no point in even talking about the t because the t distribution never approximates the the binomial distribution. But this approximation really only works if n is large enough. And a general rule of thumb is that if n times p and n times q are both bigger than about 5, then we get a reasonable approximation. And that basically is saying, do I have a picture? No. Basically, it's just saying that if p or q are too far towards the edges of the distribution, so towards 0 or towards 1, then we're not going to get a very good normal approximation because normal is symmetric and it would extend into the range above 1 or below 0. We'll see an example later on where we can run into trouble. But usually this doesn't happen if n times p is greater than about 5 and n times q is greater than about 5. And we're also going to always assume that the standard deviation is always known. So basically we're assuming that standard deviation goes into this last set of brackets here is a known quantity, again, so that I suppose we can use the z. But we have to be aware that there's a number of approximations here. One is the normal approximation. The second is the fact that we're approximating this standard deviation with p hat and q hat in that expression. Okay, so let's illustrate this with an example. Let's suppose we've got a soil compaction problem, and on a highway project, 10 out of 50 specimens suspected do not pass the DOT requirement, Department of Transport requirement. We want to estimate the actual proportion of soil that is well compacted. Okay, so we're trying to estimate P is the proportion of soil that is well compacted. We're told the ones that are not well compacted, that didn't pass. So we're going to have to invert this information here to estimate the P value. And then we want to establish a 95% confidence interval on P. Okay, so for a 95% confidence interval, alpha is 1 minus 0.95, which is 0.05. And we're told that 10 out of 50 samples do not pass. We want a confidence interval on the proportion that do pass, and we'll call that P. So we want to estimate P is going to be P hat is equal to the proportion that do pass, so that would be 40 out of the 50 samples, so 40 over 50, so P hat is 0.8. That means our estimate of the standard deviation of P hat is square root of P hat Q hat over N, so it's 0.8 times 0.2 divided by 50, and then the square root of that whole thing gives me 0.0566. And now I think we basically have everything we need to know. We're going to use the Z distribution for this quantity here. So Z alpha by 2, alpha was 0.05, so alpha by 2 is 0.025. And Z of 0.025 comes from the last line of the t-table, is 1.960. We already know what the sigma p hat is, and we know what p hat is, so we can just plug in the numbers now. And we find our confidence interval is 0.69 to 0.91. The fact that these neither of these endpoints are below 0 or above 1 means that this is probably a reasonable approximation. It's not going to be precise, but it's going to be reasonable. If you had seen something like this, if you'd seen a range that went 0.83 to 1.05, you know that that's not a good approximation because the largest value that P can be is 1. And if we're getting a confidence interval that goes beyond 1, then you know something's wrong with your approximation. And we would have to go back to first principles or just cut this off at 1 and recognize that we have approximations here. As I said, the usual rule of thumb is that this will work if NP hat is greater than about 5 and NQ hat is greater than about 5. Basically, it's just meaning that we've got to be far enough away from the two endpoints to avoid problems with the normal approximation. Oh, here's the picture. Okay, so if P is small, then what the binomial distribution looks something like this. It's just a series of steps, but the normal approximation to that looks like this. And we know that that normal approximation, here I should label this with the zeros. Okay, so that's 0 there, and N is somewhere out here. Okay, so the normal approximation to this is going to look like this, and so you've got a very big area to the left of 0, which can't be possible. You can't have a probability of success which is less than 0. So our normal approximation there is not going to be a good one. Anyhow, we will tend to avoid that if the product, the size of n times p, is large enough. Even if p is small but n is very large, you will still see some detail in here that starts to look like a normal distribution. Okay, well then the next question we asked earlier on in this sequence of lectures was, what sample size do we need in order to achieve a certain error accuracy in our estimate? Again, we see that the maximum error that we can have is just half the interval size, and that's the Z alpha times square root of P hat Q hat over N. And all we have to do is set that equal to the error value and solve for n, and we're all set. We can decide then from this, how many samples do I need to achieve a certain error at a certain confidence level. The problem with this is that often we want to know the number of samples before we've actually taken the samples. So we don't actually know p hat and q hat before we compute the required number of samples to take. So the question is there a worst case? Is there a maximum? What is the maximum value of p hat, q hat? We said if p hat is small, say 0.01, then q hat is 1 minus that, which is 0.99, and the product is about 0.01. If we go the other end and we let p hat be big, 0.99, then q hat is small, well, 0.01, and again the product is small. So somewhere between these two numbers, this range, there will be a product p times q which is achieves a maximum, and that occurs when p and q are both equal to a half, because a half times a half is 0.25. Okay, that's the largest value that this product can ever be. So the thing to do then is choose n samples from z alpha by 2 quantity squared times 0.25 divided by e squared. And this will give us the largest value of n that we could have, and it ensures an accuracy of e for any p hat with confidence 1 minus alpha. Okay, so let's illustrate this with an example. Suppose there's interest in testing the durability of plastic drill casings. I'm not even sure what a drill casing is, but there must be plastic ones somewhere. Drill casings will be randomly selected from stock, and each will be subject to a series of impacts. The manufacturer believes that the proportion of casings that break under the testing procedure should be less than 10%. So basically we're going to take this as an idea of what the true proportion of breakage is going to be. You wish to estimate the true proportion of casings that break to within 4% at a confidence level of 95%. Based on the manufacturer's claims, how many casings should you test to achieve your goal? And then the second part of this question is, suppose we ignore the manufacturer's claim and look at the worst case scenario, how many samples should we take to achieve, again, to achieve this goal of estimating the proportion to within 4%? Okay, so the belief is that p is less than 0.1 or 10%. And if we want to estimate p to within 0.04 with 95% confidence, then alpha is 1 minus 0.95, which is 0.05. And our target error is now 4%, which is 0.04. So we need to compute n equals z alpha by 2 squared times p times q over e squared. And we're going to assume p is equal to 0.10. This is going to give us the largest product, p times q, so the largest value of n. So it'll give us the error that we're looking for any p less than 0.10. Plug the 0.10 in here times 0.9. We've got a 95% confidence interval, so alpha is 0.05, and alpha by 2 that is 0.025. That gives us 1.96 squared times 0.1 times 0.9 divided by our error squared. Now this thing at the bottom here, if the error is small, this whole thing becomes rapidly larger because 0.04 squared is a very small number that we're dividing by. In this particular case, we end up with 216.1 samples, so we take 217 samples. Okay, so that's 217 samples are required to estimate this proportion to within 4%. That's pretty large, especially considering that the proportion is already around 10%. So we're talking about estimating to within between 6% and 14%. We need 217 samples. If we wanted alpha to be estimated within 4% for any p, we must take n equals z alpha by 2 squared times 0.25. So this is the worst case product of p times q divided by 0.04 squared, and that gives me 600.25. So we would now need 601 samples. So we need about, what's this about, where is it? Oh, about 3 times as many samples if we want to be able to estimate this for any p. Okay, then that's confidence intervals on proportions. We can also talk about confidence intervals on differences between proportions, just as we did for confidence intervals on differences between means. So we're now interested in the confidence interval on P1 minus P2. So basically we could ask, has the proportion of Canadians who are going to vote for a particular party changed as a result of something that happened? So the proportion before that thing would be P1 and the proportion after it would be P2, and we're checking to see if there's been a change. Our confidence interval follows the usual form, something plus or minus something times something. These are proportions, so z alpha by 2 is always going to go in this second something. The first something is the estimate of P1 minus P2, which is P1 hat minus P2 hat. And the last something is going to be the standard deviation of P1 hat minus P2 hat. Okay, as before, we're going to estimate P1 hat by counting the number of successes in the population 1 divided by the number of samples we took in population 1. And P hat 2 is the number of successes in population 2 divided by the number of samples we took in population 2. The variance, well, we'll start with the variance. The variance of P hat 1 minus P hat 2 is the variance of this sum. We're assuming that this is a random sample, so the observations that made up P1 hat are all deemed to be independent and independent of all the observations in the second sample, so that these two things are independent. And so the variance of the sum becomes just the sum of the variances. And remember, this minus 1 is squared, so it becomes plus sign here. And we know variance of P hat 1 is P hat 1 Q hat 1 Q hat 1 over N1 plus P hat 2 Q hat 2 over N2. And now we know everything we need to assess this confidence interval. And let's estimate this with an example. Okay, so example is a textile plant is considering a new weaving machine. Samples are taken using the existing equipment and the new machine in order to determine if the new machine results in substantial improvements. If 75 of 1,500 fabric swatches from the existing equipment show defects and 80 of 2,000 swatches from the new machine shows defects, find a 90% confidence interval for the true difference in the fraction of defectives between the existing and the new machine. Okay, so let's let population 1 be the samples from the original machine and population 2 be the samples from the new machine. We're looking for a 90% confidence interval, so alpha is equal to 1 minus 0.9, which is 0.1. And we're told that from the existing machine, we took 1,500 samples, and 75 of these were defective. So P hat 1 is 75 divided by 1,500, which is 0.05. From the new machine, we took 2,000 samples, and we found 80 of those were defective. So P hat 2 is 80 divided by 2,000, which is 0.04. And it looks like this is slightly lower failure probability on the new machine. But this could just be a function of the natural variability. We just happen to find a few more defectives out of the 2,000 here, or maybe a few less out of the 1,500 here. Anyhow, we have enough information now to evaluate the components that we need for this confidence interval. We'll start with this standard deviation. So that's the standard deviation of P hat 1 minus P hat 2. And that's given here. It's going to be the square root of the variance of P hat 1 and the variance of P hat 2, which is P hat 1 Q hat 1 divided by N1 plus P hat 2 Q hat 2 divided by N2. And these are approximations of the variances because we're using P hats and Q hats to determine them. And we plug in our values 0.05 times 0.95 for P hat 1 and Q hat 1 divided by N1 is 1,500, and similarly for population 2. And we get 0.00713 as our standard deviation for P hat 1 minus P hat 2. We've got a confidence interval of 90%, so alpha is 0.01. So Z alpha by 2 is Z of 0.05, which from the last row of the T distribution is 1.645. And now we're all set that we can plug in the numbers. P hat 1 minus P hat 2 is 0.05 minus 0.04. plus or minus z alpha by 2, which is 1.645, times the standard deviation of p hat 1 minus p hat 2, which we determined to be 0.00713. Then we get minus 0.0017 to plus 0.0217. And so we can say we're 90% confident that the true difference between these proportions lies somewhere inside this range. So we could ask, is the new machine significantly different? Well, no, because the 0 is included in this range. It's possible to have P1 equal to P2. So i.e. P1 minus P2 equals 0 because that's inside this range. We see, however, that the lower bound here is actually pretty close to 0. So there's probably a percentage. We took 90% here. I think if we tried this at 80%, we could probably say that there's an 80% probability that that the new machine is different, because this range probably would be all on the plus side. Okay, just to summarize then, everything we've so far done with confidence intervals. Confidence interval on the mean. We had two cases, sigma x known, and there we were using z alpha by 2 for a two-sided test, or z alpha for a one-sided test. When sigma was unknown, that looks like a z, but it's actually a t. Let me just clean that up a little bit. Let's just put that back in. T. Okay, sorry. So it's T alpha by 2 or T alpha with n minus 1 degrees of freedom. When we talked about differences in means, we had three cases. One where the sigmas were known, was pretty straightforward, and there we used Z alpha by 2 or Z alpha. The other was where the sigmas were unknown, and we assumed that sigma x1 was equal to sigma x2, and we pooled the data to find an improved estimate of the unknown variance or standard deviation, and here we're using t. And in this case, the number of degrees of freedom was n1 plus n2 minus 2. And then the third case that we had on this was when the data was paired. And here you want to take a look at the pairs of data and see if there's something in common between them. If there is, then it's paired data. So that means then there's a correlation between our observations. And the way to get rid of that correlation is to take differences and then concentrate on the DI values. So DI is defined as the difference between x1i and x2i. And then we evaluate, sorry, this should be D. This should be D bar. D bar. And SD, and then we proceed as we did with a single sample, so as we did for the mu x in the first case above, up here. But in this case, we don't know the standard deviation, so we're using t. Then we looked at confidence interval on proportions, and here we made use of the normal approximation to the binomial, so we always use z alpha by 2 for two-sided or z alpha for a single-sided, and confidence interval on the difference in proportions, again, making use of the normal approximation to the binomial, we use z alpha by 2 or z alpha. And that concludes the second part of the second lecture of week 9. There's one more part to go, and that's confidence interval on variance. We'll see that confidence interval variance is different now than our standard form where we had something plus or minus something times something. Okay, so I'll see you shortly.